people. Hope we're doing well today. Today in this video we're going to talk about a further application of the integral, and that is to find the length of a curve of a given function. So let's go ahead and jump right in with this one. Let's just say that this is our function f of x. It doesn't really matter what it looks like analytically for right now. I want to talk to you about the graphical. Now, if we were asked to find the area under the curve, and let's say that, from 1, and so here is x is equal to 1, to 4, okay? From 1 to 4, and let's say that we wanted to find the area under the curve. Well, the area under the curve is, relatively simple. We've done it 100 times before. And we know that when we did it, we entered into a discussion of it by approximation, right? We had left-hand Riemann sums, we had right-hand Riemann sums, we had midpoint Riemann sums, and then we had the trapezoidal rule. And so basically we had several different ways of approximating the area under the curve. And let's go ahead and do the trapezoidal for 3 subdivisions. Okay. Now, what we have here is we got to go from this point to that point, right? And our trapezoid is this point to that point, and then of course this point to that point. Now, I'm actually drawing this not because I really care about the trapezoidal rule at this point, but to basically make a point that this right here, what creates the top of the trapezoid, is actually a secant line to the curve, right? And this secant line is, from a point of basically this point 1, f of 1, and this point right here is 2, f of 2. And this point right here is 3, f of 3. And of course, 4, f of 4. Now, the reason why that's important is that the secant line approximates the curve over that interval. And of course, not only does it approximate the general sort of slope of it, and we talked about that when we entered into our first discussion about derivatives, right? The secant line was used to approximate the slope of the curve, and a derivative was gained when we took basically those 2 points, point 1 and point 2 of the secant line, and basically collapsed them onto each other by using a limit as h approaches 0. Now, we know that it basically approximates the slope, but it also approximates the length of the curve. This right here is approximately the same length as the curve so the straight line from 1 f of 1 to 2 f of 2 and the curve from 1 f of 1 to 2 f of 2 are approximately the same length. And of course, we would get a better approximation by chopping it up into more and more subdivisions, right? But what I want to do is let's actually focus right here on this second subdivision. This right here approximates the curve, it approximates the slope of the curve, and it approximates the length of the curve. Okay, well, I'm looking for arc length, right? And therefore, I'm kind of interested in how we might actually figure out the length of that. Well, the length of it, of course, would just be distance, and distance, of course, would just be Pythagorean theorem, right? And so we simply have to ask ourselves, in the abstract, not for any particular one, this right here is, of course, going to be whatever my change in x is over that particular interval. This right here is going to be my change in y over that same interval. That means that this hypotenuse right here, okay, has a very particular, and we'll call it z for lack of a better term. Now, what we have here is we have delta x squared plus delta y squared is equal to z squared, and therefore my z is equal to the square root of delta x squared plus delta y squared. So now I basically have a way of thinking about the length of secant lines, and of course you could beef it up notationally dependent upon a specific function given to you analytically, a specific interval, a specific number of subintervals, blah, 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 right? But if we want to think about it like this, this is basically what we mean by an expression, okay, that gives me the length of the secant line. Now, of course, what I want to do, and you probably have already guessed this because we're dealing with integration, is I want to figure out a way to represent the length of a secant line on basically a general subinterval, and then I want to sum it up, okay? Well, what that means is that what I'm going to be looking for is I'm going to be looking for the sum of all of those secant line lengths, okay? And of course, if you had a particular way to represent delta x and delta y, you would put the, I is equal to 1 to whatever, and you would basically notationally beef it up. But just, I'm talking in generalities right now. Okay, and I want to continue to talk about generalities because really, this right here doesn't do me much good in this particular form. So I want to see if I can actually change that. So let's go ahead and let's see if I can factor out a delta x squared, that is. And if I factor out a delta x squared, what I have in this first term is going to be 1, right? I factor out a delta x squared out of this term, and you might be thinking, there is no delta x squared in that term. Well, remember that if I'm factoring out, that's a form of division, right? And so it doesn't necessarily have to be there in order to actually successfully do that factoring, right? It's just a form of division. And now, of course, I have delta x squared. And if you don't think that this is the same as this, just distribute this delta x squared across this binomial and you'll wind up right back here. Okay, well, let's go ahead and play with this just a little bit more. And we have 1 plus delta y over delta x squared times delta x. Well, that winds up being a whole lot more useful. And of course, this, while it's in a different form, means the same thing as this up here, right? Basically, this is just that transformed by a few algebraic tricks, okay? Well, when I'm dealing with integrals, when I'm dealing with calculus, I don't deal with delta y, delta x. I deal with dy, dx. So what happens here is I'm going to transform this into dy dx squared and a dx. And I tell you what, that right there is going to be my new integrand. That right there represents the slices, okay? And it's not going to be slices of area. It's going to be slices of secant line length, which is a little bit, you're kind of like, well, that's not really slices. How can you slice something that's, two-dimensional? Or I mean, basically it's just a line. Well, what I'm going to do is I'm just going to be taking the infinite number of infinitely short secant lines across this entire interval. And for this particular scenario, it would be the arc length would of course be from A to, let's do it in general, not for this particular one, A to B. So I'm summing up all of those secant line lengths, those infinitely small, infinitely many, infinitely small secant line lengths, and I'm adding them up from A to B in order to get my arc length. The same way that you added up the infinite number of infinitesimally thin rectangles, or, you know, when you were doing area, you were doing cylinders, in order to arrive at the proper accumulation, right? And I keep telling you that integration is not area under the curve. Integration is a means of accumulation. And insofar as we can accumulate, insofar as we can represent what we need to add up analytically, and this is basically the way that we have chosen to transform this. We transform this into this so that it is sort of integrand ready, and we plopped it into the integrand, and then we're getting the sum of the infinite number of these that have this this change in y, change in x, and then dx, of course, well, I mean, it's all part of the secant line, because of course the dx popped out from underneath, right? But you need that differential right there in order to do the integral. Alrighty. I hope that was somewhat clear, or, you know, at least supplemental to how we discussed it in class. But let's go ahead and do some examples. All right, let's zoom in just a smidge. Okay, we are given y is equal to 1/3, and the quantity x squared plus 2 to the 3/2. And I want to find the arc length from 0 to 3. Well, the arc length from 0 to 3 means I'm going to be integrating from 0 to 3. We already know that. But we remember that if we're looking for the length, and I need to go from A to B, and I need the square root of 1 plus dy dx squared dx, and of course, alternatively, if you have it in function notation, it's not dy dx, it's 1 plus, you know, f prime of x squared dx. Either way, I need A, I need B. I have A, I have B. All I need now is something as is my dy dx, okay? So I'm going to take this, and I'm going to get dy dx. I have 1/3. That comes along for the ride. The 3/2 gets pulled down, and I'm left with x squared plus 2 to the 1/2. Now, of course, by chain rule, I need to take the derivative of the inside. That's 2x. So that 3 cancels with that 3. That 2 cancels with that 2. And what I'm left with is x square root x squared plus 2. Now, I'm not going to be plugging that into the integrand. I'm going to be plugging 1 plus dy dx squared. So, you know, if you want to go ahead and figure out and simplify dy dx squared before you get going, by all means, do so. And this winds up being x to the 4th plus 2x squared. Now, I'm going to go ahead, and my length is going to go from 0 to 3. And this right here is simply this piece of the radicand, 1 plus x to the 4th plus 2x squared dx. Well, it's kind of interesting, because the moment that you actually reorder this in descending order, that looks like a quasi-quadratic that is of perfect square trinomial orientation. And it is. It winds up being x squared plus 1 squared. Okay, well that's kind of nice, because I can go 0 to 3 of now just x squared plus 1. And you're thinking to yourself probably, well, what about the absolute value bars? You just square rooted a square. First of all, x squared plus 1 is always positive, so I wouldn't need it. Second of all, I know the values of x that I'm going to be plugging in, okay? And none of those, basically for both of those reasons, so doubly so, I don't need the absolute value bars. So what happens here is I integrate, and I get 1/3 x cubed plus x. I'm going to run that from 0 to 3. 3 cubed is 27, but 1/3 of that is 9. So 9 plus 3 minus 0 plus 0. And the answer is 12. Okay. Now, of course, that function was specifically written, right, so that you would get this. So it was kind of, they threw you a softball pitch. It was kind of a training wheels kind of question, even though it kind of looked awkward at the beginning. But let's go ahead and do another one. And this one as well is going to be really sort of a slow pitch softball kind of problem, because when you do dy dx, I know that I'm going to get negative sine x in the numerator. I'm going to get cosine x in the denominator. That's going to be negative tangent x. And when I square it, I'm going to get tangent squared x. Well, what that means is that when I put it in the integrand, underneath that radical, it's 1 plus tangent squared x. Oh my gosh, and of course, doesn't that just look pretty? I'm going to go 0 to pi over 4, and of course 1 plus tangent squared becomes secant squared, the square root of which is just secant. And if you remember this from the last chapter, this is the natural log of secant x plus tangent x, and I'm going to run it from 0 to pi over 4. That means I have the natural log of secant of pi over 4 plus tangent of pi over 4 minus the natural log of secant of 0 plus tangent of 0. Well, let's go ahead and do our evaluation of each of those unit circle values. Tangent of 0 is 0. Secant of 0 is 1. Tangent of pi over 4 is 1. And secant of pi over 4 is root 2, right? Because it's the reciprocal of root 2 over 2, which if you remember back was actually the rationalized version of 1 over root 2. So if you're asking for the reciprocal of 1 over root 2, it's root 2. Now this right here, okay, this whole thing winds up being the natural log of 1. This whole thing right here winds up being the natural log of root 2 plus 1. Well, natural log of 1, of course, is 0, and therefore the entire answer winds up being natural log, and of course this is, it's positive, so you don't need those absolute value bars, and this winds up being approximately 0.881 when you plug it into your calculator. Now, those were all well and good, and they're nice and tidy, and we like those. But remember, because we're dealing with a formula where you have to plop something into a radicand of the integrand, some of these are just not going to be solvable, okay? We're going to do quite a few that are solvable, but every once in a while, even on ones that are potentially solvable, we might just go ahead and cut our losses and plug it into our calculator, because oftentimes the calculator is there, to be used. Alrighty. Let's go ahead and let's do this one, and then we'll sort of fold in our calculator use as well. Now, what we have here is we need to find dy dx. Okay, well that's going to be 3 over 6x squared, or 1/2 x squared. And then this one, of course, is going to be, this is 1/2 x to the negative 1, so it winds up being negative 1/2 x to the negative 2. So that negative changes that to a minus sign, x to the negative 2. And so if you want to simplify this, this can become that. Or, you could just leave it as a negative exponent if you want. Okay, well, when we square our dy dx, that's going to give us 1/4 x squared minus x to the negative 2. And if I were to multiply that out, like if I were to FOIL this, right, you would get x to the 4th, and then the inner and the outer would basically be x squared over x squared, and they would both be negative. So you would have 2 of those, and then 1 over x to the 4th, or of course x to the negative 4th, whichever is your fancy. Okay, now I've done a little bit of preliminary stuff. Let's go ahead and plop it into our integrand, into our formula. So we have 2 to 4, right? That's the interval we're focused on. And we get square root of 1 plus x to the 4th minus 2. And of course, sorry, I forgot that 1/4 right there. Very, very important. X to the 4th dx. Now, You're thinking to yourself, how in the world am I ever going to simplify all that? Blah, 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 blah. Well, I got an idea. Let's take out the fraction. And if I take out the fraction, the square root of 1/4 is 1/2, right? Well, that means that I need to take it out of both terms, right? And as long as these parentheses are right here, I really have two terms in this radicand. One, and then this whole nasty thing. Well, if I take 1/4 out of here, what I'm left with is just what's left in the parentheses. But if I take a 1/4 out of the 1, how many 1/4 are in 1? And the answer is, of course, 4. So I have 4 plus x to the 4th minus 2 plus 1 over x to the 4th. Now, all this 4 is going to do is it's going to change this, and it's not going to change the fact that it's a perfect square trinomial, but it's going to change it from a minus to a plus. So what we get is x to the 4th, when I combine like terms, plus 2 plus 1 over x to the 4th, which is still, sorry, I forgot my differential out here, which is still a perfect square trinomial. And I get 2, and I get the square root of x squared plus 1 over x squared, right? So that 4 basically just changed the middle term of that perfect square trinomial and transformed it from x squared minus 1 over x squared to x squared plus 1 over x squared, but it's still a perfect square trinomial. And I have 1/2 the integral from 2 to 4 of x squared plus x to the negative 2 dx. Yay! Alrighty, let's go ahead. Now all of this, of course, all of this up to this point, from here all the way to here, none of it has, of course, been, gosh, that was a horrible brace. None of it has been calculus, but here is the calculus step right here. 1/3 x cubed, right? That's how x squared anti-differentiates. And then this becomes x to the negative 1 over negative 1, so minus x to the negative 1. And I'm going to run it from 2 to 4. Okay. Well, I mean, the arithmetic winds up being relatively, it's just fractions. When I plug in 4 into here, I'm going to wind up getting 64 thirds minus 1/4. And when I plug 2 in, I'm going to get 8 thirds minus 1/2. Well, let's go ahead and distribute this negative. Okay, and you're going to get 64 thirds and negative 8 thirds, which is going to be 56 thirds. So that's 1/2 and 56 thirds. Then you have negative 1/4 plus 1/2. That's going to give you a positive 1/4. And after a little bit of simplification and getting common denominators and all sorts of fun stuff like that, we get 227 over 24, which I won't keep you in suspense, is approximately 9.458 when you get into your calculator. And you're thinking to yourself, surely not. Okay, well, let's go ahead and let's do it in the calculator. Now, this, of course, is going to be my y1. So let's go ahead and replicate that. 1 over 6. X to the 3rd plus, let's go ahead and do 1 over 2x. Now, I'm going to go ahead and delete this right here, but remember that your calculator does integrals, but it also does derivatives at particular values. But here's the thing. If you don't want to do it at a particular value, you can use that, so second F2, and you have the derivative, and you want to do the derivative with respect to x of whatever's in y1. But since you don't want to do it at a particular value, you just do it when x is equal to x. And now, no matter what problem you're doing, the y2 will always be the derivative with respect to x of y1, which is kind of cool. So you can go back to the home screen. I don't know how much of that you got into last year. It's not earth-shattering stuff, but it's kind of cool the first time you see it. So let's do the integral, and in this case, of course, we're running from 2 to 4 of the square root of 1 plus, and the derivative, of course, is actually and usually it's probably not a problem, but I'm kind of a stickler about wanting to put parentheses. Let's go ahead and put y2 squared And that is 1 plus dy dx, because y2 is the derivative of y1. That's the way that I've constructed it. Ta-da! And there you go. Okay, and the great thing is that if you do problem after problem after problem, you know, and you just change y1, and then you can just go up and grab it, and then just change the limits of integration accordingly. Okay, that brings us to the end of our first video. I don't know, probably one more video in terms of the amount of stuff that I have left to show you. But let's, yeah, I'll call this one quits, and shoot me an email if you have any questions. Bye.